Hi everyone, I'm Komal, and today we're going to be talking about determining the equations of motion, or EOMs, of our rocket. Our goal is to analytically figure out the final altitude our rocket will reach. Before we get started with the fun math, however, let's take a step back and talk about some terminology. Just for convenience, we want to talk about our rocket's flight path in two halves. You may have heard these phrases before, but we'll define boost phase as the initial part of our rocket's flight when it's experiencing a thrust force due to our motor as well as gravity. Right after that, we have our coast phase, and this is when the motor has already burnt out and now the rocket is decelerating due to gravity. Eventually, at the end of the coast phase, gravity will cause the velocity of the rocket to be zero. This is actually how we can identify apogee. Finally, the acronym EOM stands for equation of motion, and so when we say we're solving EOMs, what we really mean is we're solving for rocket motion parameters or flight parameters such as velocity or height. Alright, now let's move on to talking about the law of physics we'll be using. From the last video, we know that Newton's second law of motion tells us that force is directly proportional to acceleration, or F equals ma. This law is the basis of how we'll calculate a rocket's final altitude. As we mentioned before, we want to see how high our rocket will go. However, as we're designing our rocket, we only know a few things: our mass, the thrust force, and the amount of time the thrust will act for. We're now going to dive right into using these quantities to determine the final height of our rocket.
Hi, my name is Hong Yong. We'll now talk about the forces acting on the rocket, which we need to calculate our acceleration using Newton's second law. Let's draw our free body diagram. A free body diagram is a diagram where you draw all the external forces acting on the system you want to analyze. As I mentioned earlier, we're assuming that the rocket goes through a one-dimensional motion, just straight up and down. So all the forces point along the vertical direction. And as you can see in our free body diagram, the forces at play are gravity, denoted as Fg, thrust, denoted as Ft, and drag, denoted as Fd. Adding up all the forces and solving for acceleration yields this equation. Acceleration equals force of gravity plus thrust plus drag divided by mass. Notice anything about the acceleration here? It is not a constant. None of the terms on the right-hand side of the equation are constants, but rather they vary with time. We are denoting this fact by writing Fg parentheses t, Ft parentheses t, and etc., meaning that they are functions of time. As for why that is, let's go through all the factors starting with mass. Mass is definitely not a constant, since it decreases as the rocket burns through its propellant and ejects it through the nozzle. Thrust is also not a constant. If you look at a motor's thrust curve, you can see that the thrust output varies throughout the flight. And that thrust goes to zero well before apogee is reached, resulting in quite a big change in the rocket's acceleration. Drag is also not a constant. Drag is a function of velocity. Imagine putting your hand out in a car window at 20 miles per hour versus 60 miles per hour. The force you would feel from the wind is wildly different. And the velocity of the rocket changes dramatically during the flight, so different amounts of drag is experienced throughout the flight. This spells trouble for us, since the two kinematic equations we introduced earlier on assume that acceleration is constant. So what are we going to do? Oftentimes in engineering, we make assumptions to make your calculations easier or possible in the first place. This does alter the problem you're trying to solve, and your results will not be 100% accurate. But as long as your simplifying assumptions doesn't deviate from reality too much, your calculated results should be close to the real one. First, it means to make assumptions about our forces and mass so we satisfy the constant acceleration condition, allowing us to use our kinematic equations. Now, we can still obtain pretty accurate results if the assumptions we make are reasonable. First assumption we're going to make is a constant mass assumption. This is a reasonable assumption for us. We're flying a small rocket motor with propellant where the propellant constitutes a small portion of the rocket mass. Now, if you're dealing with rockets that go to space, this will be a terrible assumption since most of their mass is propellant. The second assumption is to neglect drag. This is a popular assumption in most high school physics, but is this a reasonable assumption for us? Well, you will find out in one of our future videos where you will compare the real-life data with the calculated results. If they're close, then assumption 2 was pretty valid. Now, the third assumption is that the rocket motor produces a constant thrust while it burns. In reality, a rocket motor's thrust varies with time, but assuming that this thrust is constant is not totally unreasonable. After all, the thrust output does not fluctuate wildly up and down once the motor is lit. Moreover, assuming constant thrust force is the last piece in order for us to use our kinematic equations. With all these assumptions in mind, we get a new expression for the acceleration, where all the terms are constants. Well, sort of. We assume the constant value for thrust when the motor is burning, but thrust goes to 0 when the motor burns out. To reflect this, we need to make thrust a piecewise constant function, which means that it will have one constant value for one time interval and another constant value for another time interval. In the first time interval, the motor is burning, so Ft is included in the expression. For the second time interval, the motor is no longer burning, so Ft can be excluded from the expression.